All right, so last time we did talk about absorption refrigeration. I just wanted to highlight, maybe I'll touch on it again. You can have an absorption refrigeration system that requires no motor to drive a pump even. So you can run a refrigerator off of a flame, just a flame. You can have kerosene or propane refrigerators. And the kerosene you just burn, and the propane you just burn. You don't necessarily use the propane as a refrigerant, it's as a fuel. Now those are a little more complicated. If I have time, maybe I'll talk a little bit about it. But last time we introduced the absorption refrigeration, which is more of a larger system, and it uses a pump. It does use electricity to run a pump, and that's very efficient. But it will not use electricity to run a compressor. That is more expensive. All right, then we'll heat pump and gas refrigeration and some other topics of interest. So what about a heat pump system? You have to have an evaporator or condenser. Put it up here. Here's the evaporator. Come out of the evaporator. You'll put into a compressor. And from the condenser through an expansion valve. But you say that's exactly the same components as refrigeration. It is, so you can have a vapor compression refrigeration system as well as a vapor compression heat pump system. The only thing is this is what you desire, a dumping of heat to a high temperature instead of removing heat from low temperature. And this is the work to drive it. And you can define the coefficient of performance for a heat pump is what you desire, Q sub H, divided by what is cost to run it, W. What was the coefficient of performance for a refrigeration cycle? We want heat removed from the low temperature, and you have to provide power to run it. What is the first law for this system? First law for the system says that Q sub H, the only out, is equal to Q sub L plus W, the two ends. Okay. Well, you can replace right here, and you could put Q sub L plus W divided by W. True? And then you get that very startling result, 1 plus Q sub L over W, and you say Q sub L over W, isn't that? Yes, it is. So the coefficient of performance for a heat pump is equal to 1 plus the coefficient of performance for a refrigeration system operating at the same temperatures, same systems. It's just the perspective. What do you want? Gas refrigeration, let's go ahead and put a compressor, and then the gas come out and go into a heat exchanger. It's not going to condense it because it's gas. It's not a vapor that then gets compressed, that then at high pressure, when it's cooled, it liquefies, so it's not a condenser. And then here's another heat exchanger. It's not an evaporator, but it's like an evaporator, but it's a gas, so it's picking up the heat at the low temperature and dropping it off or pushing it out at the high temperature. Well, what else is there? Well, because it's a gas and it's still a gas, it's pretty easy to envision a device which drops the pressure and extracts some energy out of that process to help run the compressor. So this will be like on a common shaft, and then this shaft will have to be driven by electric motor. So this is a turbine. You still have the high pressure side. Let's say this is state, whatever you want your numbering system to be. You can number 1, 2, 3, 4. These are high pressures. Pressure 2 is equal to pressure 3 is the high pressure. And pressure 1 is equal to pressure 4, equal to low pressure. And you have some work that's out of the turbine, and you have the work to drive the compressor, and the work net is the compressor minus the turbine. And that's, as you might expect, the difference in enthalpy. It would be H3 minus H4, and this would be H2 minus H1. But this is for gas. It's just basically a Brayton cycle. It's a Brayton cycle, right? But instead of burning a fuel to then expand it through the turbine and get more work out than what the compressor had to put in, this is just opposite. You're having to put in shaft power out of a low temperature right here. What does it look like on a property diagram? What property diagram would you like to put it on? Temperature entropy. What does of constant pressure look like? It's sloping up, right? And so if we start with a low temperature here, whoops, I need to put it somewhere else. All right, let's put it right here. This is state 1. And what do we do? To state 2. But then from 2 to 3, you're cooling it to 3, to 3, and then to 4, you expand it. And this is your lowest temperature at 4. And this provides the cooling 4 up to 1. And then you have heat rejection from 2 to 3. And that's what it would look like. You ready to solve a problem with gas refrigeration?
Are 1 and 2 and 3 and 4 isentropic?
You can have it, or they can give you an isentropic efficiency of that compressor. If they give you the isentropic efficiency of that compressor, out there it goes. And if they give you the isentropic efficiency of the turbine, where is clicker question? This is now 4S straight below. Will 4 actual be in this region? Answer A. Or in this region? Answer B. Hopefully everybody has it. Let me give you a little extra time. So you have 1 minute. Where is now, if I have an isentropic efficiency for that turbine, where is 4 actual? Is it a little to the right of 4 isentropic or a little to the left? If it's a little to the left, answer A. If it's a little to the right, answer B. Here's a hint. If you have irreversibilities, is S4 going to be greater than S3 or less than S3? Greater, because you have entropy. Yeah, it's his right there. Yeah. Thank you for bringing that down. And so it's going to be B, isn't it? It'll be over B. So good to the 19 students that got that one. Okay, so a gas refrigeration cycle has a compressor pressure ratio of 4. So that's the P out over the P in is 4. And at the compressor inlet, the pressure and temperature given for air, you're just going to use air, 100 kilopascal, 270 Kelvin. The temperature at the turbine inlet is 315. So it's once it's compressed, then it's cooled, and then it goes into the turbine and it expands. And when it expands, it'll come out lower temperature than 315 Kelvin. The compressor and the turbine have isentropic efficiencies of 82 and 85%. Determine the net work input per unit mass of the airflow. So that's the lowercase w net, which is lowercase w to drive the compressor minus what you get out of the turbine to help contribute back to the cycle. And we just did those as delta H's. All right, what is the cooling per unit mass of airflow? Well, this is a gas refrigeration cycle, so that will be Q in the low temperature, and it's per unit mass of the airflow. And then what's the coefficient of performance? Coefficient of performance of this refrigeration cycle is what you desire divided by what it costs to run it, what you have to provide to run it. All right. All right, let me do this. I have it solved on the next page. Go to the solution. Here's the solution. So this is the heat exchanger that provides the cooling. And the cooling is proportional to H1 minus H4, or it's equal to H1 minus H4, the difference in enthalpy. If you wanted to, you could actually get the heat rejection, QH, which is going to be H2 minus H3. That's how much heat is rejected. All right, so the W to run the compressor, the lowercase w, will be H2 minus H1, and the work out of the turbine, specific work out of the turbine, H3 minus H4. So everything boils down to the enthalpies. You have to get the enthalpies. So you can see that I did it in Excel, and what I did was I assumed constant specific heats with the K of 1.4, pressure ratio of 4. Here I put K and then K minus 1 over K. So I put in the pressures. It goes up by 4 and then down again. So 100 kilopascal, 400, 400, back to 100. The temperatures was given this temperature. How do we calculate from 1 to 2S? Well, T2S divided by T1 is equal to P2 over P1 to the K minus 1 over K. We've done that. Ideal gas, isentropic process, constant specific heats. And then once we have T2S, then we know W compressor isentropic, which is some C sub P T2S minus T1. And then the work of the compressor actual would be 1 over the isentropic efficiency of the compressor, work compressor isentropic. Are you engaged, or am I leaving you in the dust? Is it okay? Okay, good. And so what you do a little algebra, and you find that T2 is equal to T1 plus T2S minus T1 divided by the isentropic efficiency of the compressor. So basically this equation, look at it, if eta is 100% isentropic efficiency, then T2 is equal to T2S. But as eta goes up, eta goes down to like 90%, then T2 is going to be greater than T2S. Okay, so that's how we calculate both of those temperatures. Notice 430 is greater than 401. And then you cool it to a specified temperature that was given. 315 was given in the problem statement. And then to do the same thing, you expand, but then you adjust for the isentropic efficiency of the turbine. And so it doesn't come out as cold, it comes out 227 versus 212. Once I have all those, then these delta H's are C sub P T2 minus T3s, etc. So I calculate the work of the cycle network here. I'm going to be using a constant specific heat. I believe it was 1.005 kilojoules per kilogram, degrees K or degrees C. times those delta T's to get the work net. Here's the cooling. Take a look at that coefficient of performance, about 0.6. Gas refrigeration typically is lower coefficient of performance than vapor compression. How many people think they have a gas refrigeration system in their home or in their automobile for their air conditioning, or in their refrigerator, freezer in their kitchen? Nobody does. They're all vapor compression, right? Now, there is discussion of CO2 as a working fluid in refrigeration systems, and a lot of people are working hard to see that come about. Why? It's not from a performance point of view, it's from a holistic environmental perspective, like what's you can release that refrigerant out and it doesn't have an impact, like releasing even some of the newer refrigerants, like 134A. Okay? All right. What happens if you replace that turbine with an expansion valve? Will it work? So here's a question for you. And answer A is it'll work, and it'll work okay. Answer B, it will not work. It'll be, let's just see what you say to that. Can I take that turbine and replace it by an expansion valve? All right, let's do this. Let's go to this property diagram. What is one of our favorite property diagrams? Temperature entropy property diagram, true? And let's put on a line of constant pressure and a line of constant pressure. Maybe I shouldn't make those so dramatically different slope, but they spread a little bit like that. Okay, now, this is the low pressure. This is the high pressure, true? Let's go ahead and put our states 1, 2, 3, 4 on it with the turbine as our component and not try and replace it yet. And so we had state 1 here. Then we're just going to go to isentropic. Then we'll cool it. Now, where do we want to cool it to? Let's cool it to somewhere a little bit above. Temperature at 3 is above temperature at 1. See that? How I tried to stop where 3 is? And then we'll expand, so 4 is down here. And so the cooling, it's like this is T4, this is T1, way up here is T2, and this is T3. See that? All right. Now, we said that if we have some isentropic efficiency for that turbine, it will kick out state 4 here. Maybe that was 95% isentropic efficiency. Maybe it's 90% isentropic efficiency. Maybe it's 50% isentropic efficiency. Well, just keep playing the game, right? Where is that? Where are you going to walk state 4 out to? Okay. Let me ask this. What is true about some properties between state 3 and state 4 for that expansion valve? It's H3 equal to H4. True? If we assume constant specific heats, C sub P is equal to a constant. What else do I know about another property at 3 and another property at 4? Is S3 equal to S4? Just make a list of all your properties. Start with P, T, V, U, H, S. True? We just said, hey, we've studied these expansion valves. I know what the change in H is across that expansion valve. There isn't. It's isenthalpic. I also say it's an ideal gas, constant specific heats. What other property is constant across that valve? Temperature. Do you see the little logic there? Temperatures. Okay. So if we put an expansion valve in there, where is state 4? Horizontal. It's the same temperature as 3. Guess where 4 just went? Is that going to work? Ain't going to work. No, it's not going to work. It will not work. You cannot replace that turbine with an expansion valve and gas refrigeration. All right, let's see how we did. Uh-oh. So, oh well, I don't know how to grade that. Just leave it alone. Okay, but did that explanation help? All right. So somebody says, well, I think if you can cool down to 3 to here, then it'll still work. Yeah, it'll get that much cooling. But guess what? Somehow you had to reject heat. It ain't going to work. It's not going to work. You just go in a circle chasing your tail. All right. Let's talk a little bit about liquefied natural gas. LNG is the acronym. LNG. Well, this is common, and I think you'll see more of it in your lifetime if you work in the energy sector area in Texas. So natural gas, which is CH4, they would like to be pure CH4, but it's hard to get anything pure, but predominantly methane, CH4, can be liquefied. Now, if you pressurize it, you can liquefy it at a higher temperature, but you don't like to have it at a high pressure. So at around atmospheric pressure, at a temperature of around negative 161 degrees C, that's cold, you can have it liquefied. This is minus 259 degrees F at atmospheric pressure. So what happens is they'll have a very well insulated tank, very well insulated, and they'll pump in liquefied natural gas. And if they didn't have a vent, if there was any heat transfer, you can't have perfect insulation, and if it's so cold and you have it outside, it's going to have some heat transfer into it. Okay, well, you'd minimize that heat transfer by having it insulated, but when it has some heat transfer into it, either you have to vent some natural gas or do something with it to keep the pressure constant. So they could vent it off and use it as a fuel somewhere, or just vent it off into the atmosphere. But if you plug this up and you had heat transfer into it, the pressure is going to go up. You better have a very strong container. All right. Well, San Antonio Business Journal. This is 2014, so last year. Some company, HACO, building a $91 million plant to convert Eagle Ford natural gas to alternative fuel. And you can take a look at Dallas-based company, build almost $100 million plant east of San Antonio that will produce liquefied natural gas, or LNG, for use by operators in the Eagle Ford shale oil and gas play. So here's San Antonio, there's I-10, Seguin, I-10, Schulenburg, Luling, and off to Houston, and right there's, in that vicinity is where they're building it. Between, I think it's Yoakum and Hallettsville. I have not driven out there to see it, but that's a pretty still active area of the Eagle Ford Shale. Well, a lot of areas are still active. Okay, so they expect to break ground in May or June and convert natural gas extracted from the shale into LNG that can use to fuel drilling rigs and hydraulic fracturing equipment used in that vicinity. And it's not going to be a big employer, 8 to 10 people, but that's interesting, isn't it? It'll be one of the first sites that actually make LNG for consumption in that same vicinity. And so instead of pulling out a big diesel tank and running all of those big motors off of diesel, they pull out an LNG tank with a semi, park it there, and it'll hook it up and fuel all of those big hungry diesels engines. So this is a discussion of that same plan for the Eagle Ford LNG plant. It's a first facility dedicated to put LNG into the energy exploration, extraction sector. So it's dedicated not to move liquefied natural gas where they can't construct a pipeline. If you typically you turn natural gas and liquefied natural gas so you can move it when you can't build efficiently a pipeline. Let's say I want to move it across an ocean. That's where you use it. Okay. But if you can put a pipeline in, it's much more convenient to put a pipeline in. But this is so they can take it with a semi out to a site, park it, and then for a week they'll run all the equipment off of it. All right, so here's another company, Stabila. This is out of off of their website. They're planning and building a new LNG plant as it's going to fuel the high horsepower frac and drilling engines that you can just switch it from the diesel to natural gas. It'll run it with modest changes. Okay, so they're building a 100,000 gallon per day LNG production facility in George West. Well, right, they kind of show you a little marker where George West is. It's more toward Corpus. And I'll show you a map in a minute where George West is. And they're going to be in the first quarter of 2015, so it may be up and running. I don't know personally, but they're going to be feeding all that oil field equipment using the fuel from the oil field. LNG is ideal fuel for high horsepower engines in the oil field because it's cheap, essentially low cost natural gas. And we're seeing cost savings or fuel savings of about 30% on the jobs, which is enough to make that switch. Here's another one. A new LNG terminal will export. This is common. So usually you build a facility to receive LNG or to export it. And they're going to export the gas that we're pumping out of the ground just around here. So here's an interesting way of seeing it. Customers in Louisiana pay around $2.40 per MMBTU of natural gas. Per energy content, that's what you pay. But if you can get that to Tokyo, you can get $13.50 for the same amount. It's a big price difference. It's almost 6 times the price difference. So that's why they build pipelines to move it to where some customers are willing to pay good money for it. But when it's too expensive to build a pipeline, there's no pipeline going from Saudi Arabia to Tokyo or from Houston to Tokyo. Anyway, so they liquefy it, put it on a ship, then they can move a lot. And then they vaporize it when they take it to a facility there. So what we're seeing now, the last couple of years, is building of export terminals. So they have to refrigerate, to chill, to liquefy the natural gas. So this one will take that Eagle Ford gas, convert it to LNG, and export it overseas. Where are they going to build this at? The new Corpus Christi LNG export terminal will be able to handle that many MMBTU of LNG per year. It'll be in La Quinta Channel. Anybody know that part of Corpus pretty well? Yeah. And far side of Corpus Christi Bay. Look at this. $11.6 billion facility. How much was that facility in Lavaca County? 100 million. How about by George West? Probably 100 million. almost 12 billion. Somebody's investing a lot of money. That is not the federal government investing in that. That's private money. Okay? So, this is where I believe the proposed LNG terminal off of their website, or some website. So here's Port Lavaca, here's Seadrift, Port O'Connor. Here's another one. This is a different one, Freeport. So the Freeport you can read about, they're building an LNG liquefaction and export project terminal. There's more to be checked out about it. I don't know how much the people are investing in it. But here's the one by Corpus. Well, there's probably one I missed. Okay, here's George West land. Here's up by Lavaca County. Here's in Freeport. There's the Port Lavaca, and there was one down by Corpus that I missed. It was in the last 10 years, somebody would say we're going to be building export facilities for liquefied natural gas in Texas. They would say, nah, you're joking. 10 years ago. No way. Now, nitrogen expansion cycle enhances the flexibility of small-scale LNG. How do they take natural gas and liquefy it? How do they get it so cold? That's a refrigeration project problem, isn't it? Okay, while mixed refrigerant, MR, acronym, cycles dominate the world-class and medium-scale LNG plants. So if you're building one big and it's by the coast, that's the style you're going to use. But a reverse Brayton nitrogen cycle, what? Think about that. Hey, isn't that what we just covered? Reverse Brayton gas refrigeration cycle has enjoyed a resurgence at small-scale LNG plants. Okay, so this whole article, you can find it and read it, but inside that article, they had this table. Okay, what does the table show? The specific power of different liquefaction processes. So take a look at the specific power. Let's see if we can understand that first. Specific power. Look at the units. Kilowatt hour, that's amount of energy, per metric ton. Well, metric ton is amount of mass, true? So you tell me what you think this specific power is. I'm going to pause. I want you to write it down. I want you to struggle with it. Here's a table, very easy to understand. It's applicable to what you learned in this class. They're talking about the nitrogen refrigeration cycle. It's a Brayton cycle in reverse. So you write down what it is. I'm going to walk around. Well, what would be a good metric for the system? Remember, what do we have? High-level system. I have a black box like this. And what do I have come into the black box? Some mass flow rate of methane, CH4. What do I have come out? Some mass flow rate of methane, CH4. But something's very different about this one. This is coming out at negative 100 and some odd degrees C. It's liquefied natural gas. I'm putting into a black box a stream of natural gas. It's coming in warm, it's coming out liquefied. There's a lot of heat removed. And what do we have to put into that black box to make it work? Some power. And I know there's a bunch of Q dots. You can have it different places in your cycle, but there will be one big Q dot rejection out of that cycle, out of that black box. True? So this specific power is I would like a lot of cooling, a lot of mass flow rate of the LNG coming out, but I would like a small amount of power to provide. So if you look at it, lower is better, isn't it? larger is worse for this metric. They could have inverted it and they would have a different metric, but somebody probably is the first and they did it, and that's set the benchmark. So this one would be the work per amount of LNG produced. If I could get the enthalpy in, and if I could get the enthalpy out, true, could I multiply the mass flow rate of the LNG that times the enthalpy in minus enthalpy out? Is that the rate of heat transfer that has to be removed out of the LNG to make it, the natural gas? Yeah, that makes sense. All of this work plus that out of the LNG is what's going to be dumped back off because energy is conserved. So Q dot out of the system will be the sum of W dot plus Q dot LNG. True or false? Does that make sense? I just have one mass flow rate going through the system. The LNG comes in warm, goes out really cold. Could there be some pressure change? Yeah, but the energy is, the enthalpy is really dependent on the temperature, and you liquefied it. Okay. So here is a very simple system. It's a nitrogen expansion system. And we want you, with the tools that you've been equipped with in Thermo 2, to estimate the specific power for this nitrogen expansion system. So you bring in, let's familiarize ourselves with this. What is this? Natural gas feed. What is this? LNG. All right? We talked about what temperature it needs to be at. It needs to be like negative 161 at 1 atm. So this needs to be, let's just throw a number out. I want it negative 170 degrees C at 1 atm or 100 kilopascal. Let's put 100 kilopascal. Does that make sense? It's below. I'm just throwing out some numbers. What do you think the temperature of the natural gas coming in at and the pressure of the natural gas coming in at is? 100 kPa. So really the job of this blocks is not to pressurize or depressurize. It's 100 kPa and the temperature of 25 degrees C. All right. This is a turbine. This is a compressor. So the gas, the nitrogen gas, goes in a loop. The nitrogen goes through the compressor. Then it goes to a heat exchanger. What's it doing with the heat exchanger? It's dumping heat to the air, atmospheric air. Okay? And then once it's cooled off after the compressor and after the heat exchanger, it goes through the turbine. What's going to happen to it? It's high pressure coming into the turbine, but it's going to expand. Now it's really cold. See, that's the gas refrigeration cycle. And then you put it through. Now, I'm not going to worry, and as engineers do have to worry, that it's always going to be colder than the fluid in this countercurrent heat exchanger. But I'm going to just ignore that. I'm just going to say it's cold coming in. Okay, how cold do you think this nitrogen coming in has to be? You have to, this is the hard part. You're an engineer. Could it be negative 150? Negative 100? Is that going to work? What temperatures do you think the nitrogen coming in? Negative something. Let's put it lower than negative 170, true? So what number do you want to put it at for the... I think I picked negative 172. Don't ask me why. I should have probably picked negative 175 or negative 180. But it better be colder, otherwise the system's not going to work. All right, what temperature do you think it's going to come out at? Well, it'd be more efficient if it came out at 100 degrees C. That ain't going to work. There's got to be some cooling of the 25 down, right? So what is the temperature that this can come out at? I picked 15 degrees C. About 10 degrees lower. Okay? All right, we can always change these numbers in a minute. Okay, so now I have to pick some pressure. Now, I pick 100 kilopascal and 100 kilopascal for that. But what happens when I go across this compressor? I beat it up. There's a big pressure ratio. The higher the pressure ratio, the higher the temperature coming out of the compressor, right? How big of a pressure ratio should I pick? Well, that's a hard question to answer. Let me do this. What temperature do I think I can cool it back down to after it goes through this heat exchanger with ambient air? What temperature do you think I can get that nitrogen back down to before I put it into the turbine? What temperature? 25 degrees C. This tells you something. 25 degrees C and negative 172 degrees C tells you something. Can you tell me the pressure ratio across that expander, the turbine? Can you estimate it? Can you do it right now? I'm going to pause and I want to see how many people can do it. All right, so let me go ahead and pick it back up. Can I use some equation like this for the expansion through the expander that T, I should number these, shouldn't I? Let me call this 1. I don't like that numbering system. 2 to 3 to 4, but that's what I'll do. So T1 divided by T4 is equal to P1 divided by P4 to the K minus 1 over K. How many people use that? Yeah, that's the way to go, isn't it? And so this temperature that you put in at T1, you add 273, so it's about 100 Kelvin. 101 Kelvin. This is around 298 Kelvin. And so the pressure ratio, P, the 1 over P4 is equal to T1, 101 divided by 298 to the power 1.4 divided by 0.4. Is that right? And what number does that give us? 0.00227. P4 divided by P1 is around 44. Reciprocate it. Got it? This pressure at 4 needs to be high. It needs to be high, true? Okay. What I did was I estimated a pressure ratio of P4 over P1 to be 60. If it needs to be, by this simple calculation, a pressure ratio of 44, give it a 60 or 50 or something like that. So I just picked the number, okay? So I picked 60. But now I know the pressure here to 3, that's a pressure gain or pressure ratio across it to 60 and then back across the expander of 62. But I really need to do, I wanted to do a better job of estimating temperatures and that. So let me erase some of this, get rid of this. And just say I picked the pressure here to be 60 times 100 kPa, which is 6,000 kPa. 60 bar, yeah. And then what's the pressure at 3 and what's the temperature at 3? Well, temperature at 3, the pressure at 3, I know 6,000 kPa. What about the temperature at 2? I know that. Well, I can use a constant 1.4, but I thought, well, I'll step it up a little bit. So I used this software. It's NIST. Have I showed you NIST before? I have properties for methane and properties for nitrogen. I can set it up and evaluate. So what I did was I came in and 100 72 degrees C and 100 kilopascal. And then you can see the pressures I moved to 6,000 and 6,000. That's a pressure ratio of 60. So if I put in a temperature and a pressure, it tells me the density, it tells me the enthalpy, it tells me the entropy at state 1, which is going into the heat exchanger with the making natural gas. It comes out at 15 degrees C. Did I say 15 or 25? No, it comes out at 15. I said 15 and 100. And that's the entropy. And then what I did was I said isentropic expansion, or compression, I'm sorry, to the pressure of 6,000. That coughed out the temperature of 625 degrees C. So I didn't use the constant K, but that's an estimate. But this value of enthalpy is pretty good. So if you can, write down these values of enthalpy. 103 going in, 299 coming out, 962 coming out of the compressor. And after that heat exchanger, it's cooled back down, but what I did was I only needed to cool it down to about 60 degrees C to have the same entropy to when I expand it through the expander, I am at a negative 172. If you say I want to cool it to 35 degrees C, and it's 6,000, enter. Well, then this is the new entropy, and I'll just take and copy that. And come up here and paste it, and we're going to expand it down to 100 so it can get to negative 180 degrees C coming in. Let me just copy the nitrogen values. Go back to our workbook, paste. Okay, so let me see, do I have my numbering system right? Yeah, so that's state 1, 1 right here. True? And this is state 1. So it's now at negative 180. Negative 180 degrees C. And the enthalpy is 95. 95, round that off. Kilojoules per kilogram. How about coming out? It's at 15 degrees C. The enthalpy is 299. Kilojoules per kilogram. Okay. And then we get the enthalpy at 3, right there, and the enthalpy at 2, right there. Okay, so a couple things we need to do is what is the specific net work coming in? Is that going to be the H3 minus H2? That's the work to drive the compressor, minus the H4 minus the H1, the work to expand across the expander, the turbine. And so what is this net? How many people get 450? Now, what is that? That's how many kilojoules of work I have to supply per kilogram of nitrogen going in the loop. We wanted the definition of the specific power. It's not per kilogram of nitrogen I care about, it's per kilogram of methane that's produced. So if I know the enthalpy of the methane coming in and the enthalpy of the methane going out, then that's great. Then I can get the relationship that the Q removed from the methane, CH4, is equal to Q dot that is added to the nitrogen in that heat exchanger. And so this is the mass flow rate of the methane, I'm just going to call it LNG, that's produced, times the enthalpy difference of the LNG. Let me just leave it as delta H of LNG. And this is the mass flow rate of the nitrogen times the delta H of the nitrogen. All right, well, do we know what this delta H is right here of the nitrogen? Is that true? Yeah. 204 kilojoules per kilogram. I'm going to go ahead and go back to my ref prop and do the delta H for the nitrogen, the methane. So here it is. I said it's coming in at 25 degrees C and 100 kilopascal. So that's the enthalpy, 910 kilojoules per kilogram. And it's coming out at 170. It's going out at negative 29 kilojoules per kilogram. So let me go ahead and copy this and put it down here. Edit, paste. Ooh, I don't have much room for it, do I? Oh, I'm running out of room big time. Oh boy. Shoot, didn't want to do that. Well, hard to see, but I wanted to put it on the screen anyway. All right, so what did we get for the delta H of the LNG? 939. Okay, so the amount of LNG produced per amount of nitrogen in the loop is 204 divided by 939, 0.2173 or something. I should keep more digits, but I'm just running quickly. So what we find is that the specific power is the work net times mass flow rate of the LNG, LNG, divided by the mass flow rate of the nitrogen N2. That's my specific power, which is the 450 kilojoules. I'm messing this up bad because I'm trying to conserve space, but I have to scroll down. So the specific power is equal to the 450 kilojoules per kilogram of nitrogen times 0.2173 kilograms of LNG per kilogram of nitrogen. An hour is 3,600 seconds. A metric ton of LNG is 1,000 kilograms. So what is our estimate of the specific power? 575. That's kilowatt hour per metric ton of LNG. Very simple calculation, right? Or as simple as I can make it. So let's go back to our table, 375. How are they going to get that number lower? Well, that's the type of thing the engineers are employed to do. If you were a new engineer and they said, we just barely got this system working, but I want you to improve its efficiency, you should know from this class where you're going to attack. You're going to attack to reduce the work in. Okay? How are you going to reduce the work in? What type of enhancements did we have? That's the word I'm looking for. Who said intercooler? There you go. See? Why is that going to make it more efficient? And it's always cost less to boost the pressure of a dense fluid. It's always cost less. And so get it cool, keep it dense, boost the pressure. But as soon as you start to boost the pressure, the temperature goes up, it tries to expand. It makes it more expensive. So right here, this is way too hot. You know, this is coming out at, what was that temperature again? 625 degrees C. That's not realistic for a single stage. It would be pretty easy to have multiple stages and intercooling in between. Wouldn't it make it a lot less? It would cost a lot less. But you added extra complexity to the cycle. Here I wanted to get to typical flow schemes out of that gas processing news article of a typical nitrogen expansion process. All right, it looks pretty complicated, but we can step through. What comes in up here? Natural gas. Let's just follow it. It comes here. This is a column that it's a fractionation column. What do you think comes up out of here? Just follow this loop first. Comes through and does this, but it splits right there. What do you think this is? LNG to the tank. That's what we wanted. Okay. Well, they have an optional pump to recirculate to go back up here. Okay. Because this fractionation column, they kind of heat the bottom and they cool the top. And what this does is it's already cooled some of the natural gas. It's not at the temperature, negative 160 degrees or so, that it needs to be, but it's some intermediate temperature. Because do you think this natural gas is pure methane? No. Do you think the LNG, it's liquefied natural gas, it's much pure methane? So what happens is what is this? I know there's a lot of acronyms. NGLs, natural gas liquids. When you get the natural gas out of the ground, it has some propane, ethane, butanes, and those you want to get out of the natural gas. You can actually sometimes sell them for more money. With the ethane, you can make a lot of plastic products. It's a building block in the petrochemical industry. And interestingly, in the natural gas in the Eagle Ford Shale, guess what it's high in? Ethanes. And so even when I was talking to some people that work at Zachary about they're not only making liquefied natural gas, but they're trying to make sure that they do something, because what's Houston? Other than a big machine shop, it's a big petrochemical refining area. So they're doing all sorts of things with the ethane and other butanes and propanes. Okay? So that's what this LNG is. If they're higher carbon, so methane is CH4, right? What is propane? C3H8. It's more carbon. It has higher carbons. And so basically these natural gas liquids are bigger molecules. They will turn into liquids at a not as low a temperature. And so they can be taken out through this cryogenic process. Okay. Now, this is a big box. What color did they code this box? What color is it? Look, blue. What does that signify, the color blue? Cold. It's called the cold box. Super highly insulated. And there's a lot of pipes that come in here and there, because my schematic was, just bring it in and let it be just a single countercurrent heat exchanger. You have a bunch of loops where it's transferring heat here, then transferring heat here. But let's take a look. We have nitrogen refrigerant, okay? So it comes and you have an expander compressor and an expander compressor and a compressor. What are they doing here? Yeah, chilled water or cooling water. They're rejecting heat. So it's like having an intercooler at different places, and you have different compressors. And when you expand it, you can get it to a different temperature. But right here, the cold expander, this is the expander side. This is the compressor side. It's going to drop it to the lowest temperature, and then you try to match that temperature to have a slight delta T to keep it cold to produce the natural gas liquids, or the liquid natural gas, LNG. All right? A little warmer, they bring in another stream, and then it goes up, up, up. All right? This is what the engineer would make a lot of money on. I mean, that's his job, optimize that system. And this system I skipped over. This is a SMR, single mixed refrigerant. Too many acronyms. And you can see that they have all kinds. And if we look back at our comparison chart, here is a single mixed refrigerant. What do you think D is for mixed refrigerant? Dual, double, something like that. And then cascade. Hey, we were studying cascade refrigeration systems. And then this one is a C3. That C3 is for propane. It's a propane mixed refrigerant system. And notice that's that's great. That's your best. So it will have some propane refrigerant in there. It'll have some other refrigerants that are mixed, like maybe 134A and 410A and some other ones. But when you get to the real systems and big systems, they can get more complex. Here's a simpler one, the nitrogen recycle process. I think I covered it already, but you have the compressor, expander, multiple heat exchangers to improve efficiency. All right, that's all I wanted to cover on refrigeration. So we're done with that. Let me stop here.